When 3I Atlas reached its perihelion on October 29th, most observers expected a typical profile for an interstellar comet under extreme solar influence, a flare-up in brightness, possible fragmentation, and then a gradual fade as it moved outbound. But what actually occurred was neither typical nor easily explained. Instead of following the predictive models built by the global astronomy community, 3I Atlas displayed a smooth, subtle change in trajectory, a deviation that was almost imperceptible at first, but has now become the focal point of every observatory tracking its path. The perihelion event was initially considered uneventful. No large-scale sublimation was detected, no chaotic tail eruption. In fact, for hours surrounding its closest approach, the object held its course with eerie precision, seemingly unaffected by the intense radiation and gravitational stress one would expect so close to the sun. But buried in the post-perihelion telemetry were hints, small shifts in trajectory, minute delays in expected light curves, and unusual symmetry in motion that all pointed to something having changed. It wasn't until weeks later, when multiple observatories began overlapping their post-perihelion datasets, that the pattern became undeniable. The object had veered not wildly, not dangerously, but intentionally. The trajectory had curved in a way that could no longer be attributed to random outgassing or solar wind buffeting. The smoothness of the arc was the most telling clue. Natural perturbations tend to be noisy, jagged, chaotic. This was not. The drift was linear, graceful, almost mathematical in its form, as if following a pre-calculated path. NASA's Jet Propulsion Laboratory ran a revised orbital solution based on these deviations and quietly updated their public ephemeris. In it, 3I Atlas's new outbound trajectory showed a noticeable offset, one that projected a significantly closer Earth passage on December 19th. This wasn't just an adjustment in numbers, it was a redefinition of the object's entire relationship to the inner solar system. The cause of this shift remains unconfirmed. Natural explanations point to asymmetric outgassing, the typical cometary jets that act like microthrusters as ice sublimates unevenly across the surface. But to cause such a clean and persistent change in direction, those jets would have had to be perfectly timed, perfectly aligned, and perfectly sustained across a rotating body, a level of precision never before observed in any natural comet. Others look towards solar radiation pressure. If 3I Atlas has a highly reflective surface, possibly composed of metals or dense carbon-based compounds, then the pressure from photons could exert force over time. This would still be natural, but again, the efficiency and stability of such a process raise further questions. For this theory to hold, the object would need to have a shape and surface texture far more engineered than porous comet crusts typically exhibit. And then there's the quiet theory that this wasn't a reaction to perihelion at all. It was an execution, a maneuver, a planned correction. It's not a theory that makes its way into published papers, but it circulates in private emails and closed meetings, not because of what we saw, but because of how it happened. The change occurred not during peak radiation, not during flare impact, but in the soft corridor just after, when the data streams had calmed and instruments were not at their peak sensitivity. Whatever happened at perihelion didn't end there. It began there. It set 3I Atlas on a path that now brings it closer to Earth than any other interstellar object in recorded history, not by coincidence, but by adjustment. And that is the moment researchers now revisit daily, not because it was the most dramatic, but because it was the most precise. There's nothing inherently special about December 19th. No solar eclipse, no planetary alignment, no historical significance in the astronomical calendar. And yet, every telescope with line of sight to the outbound corridor of 3I Atlas is now locked onto that date. Why? Because the new orbital solution released on December 4th shows that this is the moment perhaps the only moment when Earth will cross behind the trajectory of this interstellar object at its point of closest approach. It's important to clarify this is not a collision course. There is no imminent threat, no apocalyptic forecast. The object will remain over 100 million kilometers away, a safe distance by any measure. But in astronomy, proximity is relative. In interstellar terms, this is practically brushing past our front porch. And for those who study anomalies, it's an opportunity that cannot be missed. The window itself is not just about physical closeness, it's about clarity, observational clarity. On December 19th, Earth's position in the solar system will place it directly in the wake of 3I Atlas's outbound path. This means telescopes on Earth will be able to observe the object from a rearward angle, catching light that passes through its debris corridor. The timing also coincides with minimal solar interference, allowing longer exposure times and uninterrupted tracking. Why does this matter? Because if there's anything hidden in the tail, structure, particles, ionized gases, or even signatures that defy our expectations, this is when we'll see them. Dust tails from comets are normally chaotic, but they disperse over time. 3I Atlas has not followed that script. Its tail has remained unusually narrow, coherent, and persistent long after perihelion. If it leaves a wake, that wake may still be intact. If it was propelled, that propulsion may have left a trail. Multiple agencies are preparing for this. NASA's Deep Space Network has already scheduled multiple signal tracking windows to gather reflected radar data. The European Space Agency has allocated emergency time on its solar system tracker program to continue passive monitoring, and ground-based observatories from Chile to South Africa are adjusting their imaging schedules to ensure they capture the post-flyby corridor. But the December 19th window also raises unsettling questions. Why is this the moment of closest approach? Why, of all trajectories, would 3I Atlas shift its outbound vector to intersect with Earth's heliocentric orbit at precisely this angle in time? The previous orbit had it exiting the system in a much wider arc, clean, non-intersecting, drifting toward the outer planets. It wasn't until the anomalous acceleration following perihelion that the object's path began to bend inward, slightly but deliberately, toward the orbital plane of Earth. Analysts are hesitant to speculate publicly, but the numbers are difficult to ignore. The object adjusted itself. The adjustment places it at an observational peak exactly when Earth crosses its trail. This is not the behavior of a passive, frozen body drifting through space. This is timing, and with timing comes the implication, however distant, of intent. Even if nothing dramatic happens, December 19th remains a scientific inflection point. It is the best opportunity we may ever have to study an interstellar object this close, this recently altered, and this potentially structured. Radio telescopes will be scanning, optical arrays will be imaging, infrared platforms will be measuring heat signatures, and all of them will be asking the same question: why now? In a cosmos ruled by gravity, most paths are predictable, but 3I Atlas keeps deviating from that expectation, not chaotically, but with quiet precision. On December 19th, we'll have one shot to understand why, because if it's trying to show us something, this is when we'll see it. When tracking the motion of objects in space, gravity is supposed to be the constant, the baseline against which all movement is measured. From planets to comets to drifting debris, the laws of Newtonian motion and Keplerian orbits generally explain it all. But 3I Atlas has continued to resist these classical models. The data now shows with mounting consistency that its trajectory is being influenced by forces that are not gravitational in origin. These deviations aren't large, they're not catastrophic, but they are persistent and they are clean. That's what makes them so hard to ignore. The object doesn't wobble or jitter or accelerate in chaotic bursts like a normal comet responding to asymmetric sublimation. Instead, it curves gently, continuously, and in a manner that suggests a stable force is acting upon it. We first began noticing these anomalies shortly after the object passed perihelion. Its outbound velocity was supposed to follow a specific hyperbolic escape vector, consistent with a passive object shedding mass as it retreated from solar influence. Instead, the trajectory began to bend outward, not sharply, but precisely. Orbital Solutions from NASA's JPL, ESA's Solar Orbiter, and multiple independent teams all began showing subtle but measurable non-gravitational accelerations. The term non-gravitational force in cometary science typically refers to outgassing, the release of gas and dust from a surface which produces a recoil effect, like a slow-motion thruster. This process is well documented in solar system comets, but those forces are erratic, noisy, and tied to temperature fluctuations across the nucleus. They cause irregular motion, uneven rotation, and instability. None of that is happening here. With 3I Atlas, the shift is too smooth, like a sail catching wind, not like a snowball shedding jets of vapor. That comparison isn't accidental. Some analysts now believe the object may be responding to solar radiation pressure in a way we've never observed before. In other words, light itself may be propelling it, not as a random force, but as a dominant mechanism of motion. Solar radiation pressure is a real force. It acts on every object in space, though usually at insignificant levels. For it to meaningfully affect an object's trajectory, that object must either be extremely lightweight, highly reflective, or both. That's the foundation of solar sail propulsion, a technology that uses the momentum of photons to drive a spacecraft forward, and it's now being used as a model to understand what 3I Atlas is doing. The math is startling. If 3I Atlas is even moderately reflective, its observed trajectory could be explained by a surface area to mass ratio that matches some of our most advanced solar sail designs. That kind of configuration isn't something we associate with natural bodies. It implies a structure, not a rubble pile. It implies symmetry, not fragmentation, and it implies persistence, the ability to maintain alignment over time. Some scientists argue this doesn't have to be artificial. Perhaps the object is naturally thin, like a flake of interstellar ice shaped by radiation erosion across millions of years, but even then, its stability would be difficult to justify. Most thin natural structures would tumble or collapse under solar heating. 3I Atlas rotates but does not tumble. It adjusts but never erratically. The most convincing evidence for non-gravitational influence is the curve itself. The force acting on the object behaves independently of its mass. It doesn't follow gravitational vectors. It aligns instead with solar vectors, meaning the object appears to be pushing away from the sun, not because it's being pulled, but because it's being pushed. That's the inversion that now dominates all discussions about 3I Atlas. It is not simply falling through space, it's responding to space. And if that response continues, it could mean the object isn't just a passenger in the solar system, it's navigating it. The most revealing movements in space are often the ones we can't see, not with the eye, not with a telescope, but only through the subtle fingerprint of motion left in light. This is where Doppler analysis becomes essential. It allows scientists to measure the radial velocity of an object, how fast it's moving toward or away from the observer, by tracking the shift in wavelength of the electromagnetic radiation it reflects or emits. It's not a photograph, it's a pulse, a signal. And for 3i Atlas, that pulse just changed. Between November 28th and December 3rd, three independent radio observatories in Chile, Australia, and South Africa recorded small but consistent Doppler shifts in the reflected light spectrum of 3i Atlas. These shifts indicated a slight repeating variation in the object's velocity along the line of sight. In simple terms, the object's motion was no longer matching the predictions, but it wasn't the change itself that sparked debate. It was the nature of the change. The Doppler drift wasn't random. It wasn't noise. It followed a pulse-like pattern, a smooth rise, a plateau, and a return to baseline, repeated more than once. That sequence doesn't match any known natural acceleration signature. There were no solar flares during those intervals, no radiation spikes, no nearby planetary influences, nothing external that could account for the motion. The acceleration seemed to come from the object itself. This drift has been described as a soft push, not explosive, not abrupt, but deliberate. Imagine watching a canoe on a still lake that suddenly, smoothly begins to move forward. Without paddling, that's the sensation Doppler analysts were left with. 3i Atlas is drifting, but not aimlessly. It's applying force in a controlled vector. Traditionally, Doppler changes in comets are attributed to outgassing, gas jets pushing the nucleus and subtly altering its velocity. But when this happens, the Doppler curve is uneven. Gas venting is messy, reactive, and causes torque. It makes the comet spin, wobble, and often change brightness erratically. Yet the object's spin rate, tracked separately via photometric analysis, remained stable. Its light curve remained clean, and the emission signature showed no increase in water vapor or carbon monoxide that would suggest a major sublimation event. This has led to one unavoidable conclusion. The Doppler drift is not tied to chaotic natural forces. It's either being controlled or it is the product of a consistent external pressure being applied across a broad surface, the kind of force you might expect from photon pressure acting on a reflective structure. Some researchers have proposed the concept of phase-lock reflectivity, that parts of the object's surface are adjusting orientation in small intervals to capture or deflect solar radiation. If true, that could explain the pulsing nature of the Doppler shift. Each change in velocity could correspond to a realignment event, like panels adjusting themselves slightly to maximize thrust before returning to rest. Others have suggested a more radical possibility, that the object is equipped, naturally or artificially, with some form of impulse mechanism that vents mass or adjusts internal balance in precise, rhythmic intervals. In that case, the Doppler data might be showing us a kind of propulsion pattern, one invisible to our eyes, but etched clearly into its motion through space. One fact remains undeniable. Doppler data is objective. It doesn't care about theories. It doesn't offer interpretation. It simply reports motion. And what it's now reporting is motion that diverges from pure gravity. It confirms that the shift in trajectory detected after perihelion is real, active, and continuing. This is no longer just a question of where 3i Atlas is going. It's a question of why it keeps adjusting how it gets there. Light carries more than illumination. It carries structure. When photons scatter off a surface or pass through a cloud of particles, their orientation can change. This effect, known as polarization, becomes one of the most powerful diagnostic tools in astronomy. It's how we detect surface textures, material composition, and quasi, more subtly, how we distinguish between dust, gas, and solid form. And in the case of 3i Atlas, polarization is once again raising uncomfortable questions. On December 3rd, a team operating the European Southern Observatory's polarimetric array reported something unexpected, a short-lived return of negative polarization, echoing the exact same signal profile detected back at perihelion in late October. The values were brief, measured in tenths of a percent, but unmistakable. And for those who understand what this signal means, its reappearance is not just surprising, it's anomalous. Most comets display predictable polarization patterns. As sunlight hits the dust in a comet's coma, it scatters, and that scattering tends to polarize the light in a very specific way, usually positive, aligned perpendicular to the incoming light. However, in comets with very fine dust or unusually compact surfaces, a brief phase of negative polarization can appear at small scattering angles. This negative branch is well understood and has been cataloged for decades, but 3I Atlas is not obeying those rules. At perihelion, the negative polarization branch, measured by multiple telescopes, was deeper and narrower than anything previously recorded in a comet, including the hyperactive interstellar visitor Tuha-I Borisov. At the time, scientists chalked it up to extreme surface processing from solar radiation or possibly the effect of unusually small carbon-rich dust grains. But now, more than a month after perihelion, the signal has returned. This shouldn't happen. The scattering angle has changed. The object has moved significantly. The coma should be dispersing and solar heating has decreased. In every model of comet evolution, negative polarization is a fleeting event, a flash, not a repeating pattern. So why is it back? One explanation is instrumentation error, but that was quickly ruled out. The December 3rd measurement was confirmed by two separate teams using independent instruments. The orientation of the polarization vector was consistent. The negative value was brief but coherent. There was no hardware malfunction, no processing error, no solar interference. This leaves only one conclusion. The object itself is continuing to reflect light in a way that suggests a smooth, compact, possibly engineered surface, and it's doing so under new lighting conditions. In other words, the negative polarization wasn't just a byproduct of a one-time solar event, it's a property of the object. This return of the signal has led some researchers to revisit an earlier hypothesis, one that many had dismissed out of caution. The hypothesis that 3I Atlas is not a diffuse, dusty snowball like most comets, but rather a structured body with surface geometry capable of reflecting polarized light in phase-dependent ways. In this model, even slight changes in the object's orientation relative to Earth and the Sun could trigger new polarization effects, especially if the surface includes materials like nickel, graphite, or carbon composites, which are known to reflect light in coherent ways. These materials aren't commonly found in natural comets, but they do exist in meteorites and in manufactured systems, and that's where the unease begins. Negative polarization at this phase angle implies more than a smooth surface. It implies reflectivity, intentional structure, coherence, and in a vacuum where nothing should be aligned, 3I Atlas is once again reflecting light like a signal, a response, not a coincidence. The echo of polarization is not just a scientific data point, it's a recurring fingerprint, one that refuses to fade, no matter how far this object moves from the sun. And if the surface keeps shining like this, we may have to stop calling it a comet at all. One of the most persistent myths about objects in space is that they're round. From planets to moons to asteroids, we tend to imagine everything as a sphere, a product of gravity molding matter into the most efficient shape. But that rule only applies to large bodies. Small ones, especially interstellar objects like 3I Atlas, follow no such blueprint. And now, thanks to detailed light curve analysis, a clearer picture is emerging. 3I Atlas is not spherical. It's elongated, possibly extremely so. Light curves are one of the most basic tools in astronomy. By measuring how the brightness of an object changes over time, scientists can infer its shape, rotation speed, and surface composition. When an object spins, its reflectivity changes depending on what part of it is facing the observer. A sphere produces a flat or gently oscillating light curve. An elongated object, like a cigar or a blade, creates sharp, rhythmic peaks and valleys as it tumbles or rotates. The light curve for 3I Atlas, observed continuously over 11 nights from multiple observatories in both hemispheres, shows a clear and repeating modulation, one that cannot be explained by surface features alone. The pattern is consistent with a highly elongated shape, rotating slowly around its long axis. But what makes it remarkable is how stable that rotation is. After its close encounter with the Sun on October 29th, many expected 3I Atlas to exhibit post-perihelion wobble, a chaotic tumbling motion caused by uneven heating and asymmetric mass loss. That's what happened with Comet Ison. That's what happened with Lovejoy. And that's what usually happens when fragile, icy bodies undergo thermal stress. But 3I Atlas didn't wobble. It didn't tumble. It rotated smoothly, almost mechanically, as if impervious to internal imbalance. This kind of rotational stability is rare. Natural bodies that are elongated tend to develop complex spin states over time, especially after solar encounters. The fact that 3I Atlas has not only retained its elongated shape, but also its precise rotation strongly suggests internal cohesion, either a monolithic structure or a rigid shell. In either case, the object is not behaving like a rubble pile, which is the standard for comets. It's behaving like a solid object. The estimated axial ratio, the proportion between the long and short dimensions of the body, is still under refinement, but current models suggest a minimum ratio of 6.1. That would make it more elongated than Oumuamua, the first interstellar object we detected in 2017, which had an estimated ratio between 5.1 and 10.1. And like Oumuamua, 3I Atlas's brightness peaks sharply as it presents its long side to Earth, then dims quickly as the narrow edge comes into view. One particularly puzzling feature of the light curve is the lack of phase damping. Normally, comets display a gradual flattening of their brightness oscillations as dust and gas obscure the nucleus, but 3I Atlas has retained a clean, high-contrast light profile, which implies that the coma is either very thin, very localized, or being actively suppressed. Some researchers are now proposing that the shape of the object may play a role in its motion, not just as a passive result of formation, but as an active component of its trajectory. In solar sailing theory, long, thin shapes offer more precise vector control. Their surface area can be aligned to incoming photon pressure to produce directional acceleration. If 3I Atlas is using sunlight as a propulsion source, even passively, then its shape may not be an accident at all. We may be looking at an object designed or evolved to optimize its interaction with radiation, and if that's the case, then the question shifts from what this object is to what it's for. In every known comet, the coma is one of the most defining features, a bright, billowing envelope of gas and dust that surrounds the nucleus as sunlight begins to heat its surface. It's the visual evidence of activity. It's also the natural outcome of sublimation, ice turning to vapor, dust being released, and particles scattering freely into space. But 3I Atlas is breaking this rule too. Its coma is present, but it refuses to behave. It refuses to grow. It refuses to dissipate. And most of all, it refuses to expand. Since its perihelion on October 29th, observers have been carefully watching the evolution of the object's coma. After such a close encounter with the Sun, expectations were clear. We should see rapid outgassing, an expanding shell of particles, and a dramatic growth in both size and brightness. That's the playbook. It's what happens with every icy body that crosses that thermal threshold. The coma typically expands outward in all directions, becoming more diffuse over time until the nucleus fades from view completely. But that hasn't happened here. Instead, the coma of 3I Atlas has remained tightly bound to the nucleus, narrow in profile, and unusually symmetrical. The latest measurements from the Pan-STARRS Observatory in Hawaii show that the coma's apparent angular width has not changed measurably in over 10 days. Even accounting for perspective shifts and distance corrections, the physical dimensions of the coma are holding steady. That's not just rare, it's almost without precedent. So what could explain this? One theory is low activity, that the object simply isn't outgassing much at all, but that contradicts other observations. The object is still producing jets, its brightness remains high, its tail is visible and growing. Water vapor and carbon dioxide have been detected. It is active, just not in the way comets are supposed to be. In other words, something is being released, but it's not blooming into a classic coma. Another possibility is a kind of structural containment, that the gases are being ejected in narrow directed flows rather than diffuse bursts. Think of it like a nozzle rather than a leak. If the outgassing is collimated, channeled through specific pathways, then the resulting coma would appear tighter, more focused, and possibly more stable over time. This could also explain the formation of sharp jets and the existence of the now documented anti-tail pointing toward the sun. But here's the deeper problem. Thermal models still don't add up. At its current distance from the sun, the surface of 3I Atlas should be warming unevenly, producing asymmetric sublimation. That process under natural conditions creates turbulence, jets flaring in different directions, the coma pulsing as fresh layers of ice are exposed. Instead, we see consistency, uniformity, control. Some researchers are starting to consider whether the coma is being suppressed not by accident, but by design. A structure with layered coatings or a crust-like surface could control how and when gases escape. Certain materials like carbon silicate compounds or irradiated ice mantles might slow the release of volatiles. There's even discussion of electrostatic suppression, the idea that charge buildup around the object could confine ionized particles, keeping them close to the core before release. Whatever the mechanism, the observational fact remains. The coma is there, but it isn't doing what it should. It hasn't bloomed, it hasn't dispersed, and even as solar energy continues to interact with the surface, the envelope remains thin, tight, and persistent. To some, that suggests a dormant nucleus waking up slowly. To others, it suggests something else, that the coma isn't the byproduct of decay, but the residue of something active, something managed, something that doesn't want to be seen too clearly until the timing is right. Every object in space obeys the same rules of heat. It takes time to warm up and it takes time to cool down. That delay is called thermal lag. It's expected, it's modeled. It's even used to estimate the composition and structure of asteroids, moons, and comets. When an object passes close to the sun, we always see the same rhythm. Temperature rises, reaches a peak after maximum exposure, and then slowly falls off as the object retreats. But 3I Atlas didn't follow that rhythm. As it approached perihelion in late October, astronomers began measuring infrared radiation, the heat signature of the object's surface, using data from both space-based and ground-based observatories. The models predicted a steady rise in temperature as the solar flux increased, followed by a gradual peak after the point of closest approach. But the data told a different story. Instead of a delay, 3I Atlas's thermal curve mirrored the sunlight curve almost exactly. As solar energy increased, the object heated up in near real time. As soon as perihelion passed, its temperature dropped immediately without the usual delay. No lag, no retention, just fast in, fast out. That shouldn't be possible for a natural object of its estimated size. Ice, rock, and dust don't heat and cool that quickly, especially when wrapped in even a thin coma of gas and particles. These materials retain heat. They release it slowly over hours or even days. But 3I Atlas radiated heat as if it were thin, highly conductive, and actively managing its thermal output. This precision forced scientists to recheck their data. Not once, but multiple times. They reanalyzed the calibration of infrared instruments on SOFIA, reran the readings from ground arrays in Chile, and cross-checked against readings from the James Webb Space Telescope. All results aligned. The object did not store heat. It didn't hold on to solar energy the way a dirty snowball would. It responded like something metallic, or better yet, something engineered for heat dispersion. This opens a fascinating line of inquiry. How is 3I Atlas losing heat so fast? One possible answer is surface composition. Certain materials like highly reflective carbon structures or even thin metallic films are capable of radiating thermal energy almost instantly. These materials are not common in natural objects. They are found in spacecraft, satellites, and thermal shielding. If 3I Atlas has a surface covered in something like graphene layers or a highly conductive carbon alloy, that could explain the rapid dissipation. Another possibility is structural. If the object is hollow or partially hollow, heat would be distributed over a larger surface area with less internal retention. This could create a kind of flash heating effect where the surface responds instantly to incoming radiation, but the lack of internal mass prevents thermal buildup. Hollow core structures are not impossible in nature, but they're rare and generally unstable, especially after solar exposure. Yet 3I Atlas has remained structurally intact. The third possibility is even stranger: active thermal regulation. Some researchers are now speculating, carefully, cautiously, that 3I Atlas may possess systems or properties that regulate temperature intentionally. That could mean materials that change phase to absorb heat, surfaces that reflect radiation directionally, or geometry designed to minimize exposure. These ideas stray into the territory of design, not just behavior. Whatever the mechanism, the implications are profound. The lack of thermal lag is more than a curiosity. It's a diagnostic signature, a fingerprint of a surface that refuses to follow natural expectations. In a universe governed by heat and light, this object is writing its own thermal script, and that script doesn't say comet, it says controlled. In the anatomy of a typical comet, water is king. As the sun heats the surface, water ice sublimates first, producing jets, dust clouds, and the familiar glowing coma. After that, other volatiles like carbon monoxide or carbon dioxide may appear, especially farther from the sun. But in all cases, water dominates the inner activity zone. It's the most abundant, the most expected, and the most modeled. That's why the behavior of 3I Atlas is so perplexing. Spectral analysis from multiple observatories, including infrared data, captured in late November and early December, confirms that carbon dioxide, not water, is the dominant volatile being released. Again, just as it was during the first active phase, weeks before perihelion. But this time, it's stronger, more concentrated, and even more difficult to explain. The data shows that CO2 is not just present, it's central. The emission lines associated with CO2 molecules, specifically in the near-infrared band, are clearly visible and outshining those of water. Vapor by a factor that defies standard cometary models. Even more oddly, the release of carbon dioxide has not decreased as the object moved away from the sun. It has stabilized. In natural comets, carbon dioxide plays a supporting role, a deeper layer volatile that sublimates only once the outer ice has been stripped away. It's less sensitive to solar heating and usually fades rapidly after perihelion, but 3I Atlas seems to be actively producing or emitting carbon dioxide from a shallow surface layer. That's an inversion of what we expect. It suggests one of two things. Either the surface is unusually enriched in CO2, or the internal structure is releasing it through mechanisms we don't understand. Neither option is comforting. One possible natural explanation is compositional uniqueness, that 3I Atlas having originated outside our solar system, formed in a carbon-dense region of space. In this model, CO2 becomes the dominant ice from the beginning, but that doesn't explain the consistency or timing of its release. Why would the CO2 only intensify after perihelion when solar energy is decreasing? Why is there no corresponding increase in dust or other gases? Another theory, more speculative, is that the CO2 is not sublimated but vented, that it's not emerging due to heat but by pressure through fixed or regulated pathways. This matches other anomalies we've seen: the stable coma, the controlled jet patterns, the repeated Doppler shifts. It paints a picture of an object that is choosing how it loses mass, not being forced into it. There's also the troubling possibility that the carbon dioxide isn't ancient ice at all. It may be a product, a chemical output of some other process. Radiation shielding, internal reaction chains, or surface processing could produce CO2 from carbon-bearing materials under certain conditions. If this is true, then we're not observing sublimation, we're observing transformation. Whatever the origin, the dominance of carbon dioxide raises critical questions. Why is it rising while water remains subdued? Why does it follow no thermal delay? And why does the outgassing pattern remain stable, almost as if regulated? This isn't the first time astronomers have seen CO2 dominate unexpectedly. Oumuamua had similar traits, although never confirmed directly. But with 3I Atlas, the pattern is clearer, more measurable, and more persistent. It's not a single flare, it's a sustained signature. And when an object behaves as though its chemistry is under control, when the most volatile compound acts less volatile than the rest, we're forced to confront a possibility that no telescope is comfortable saying out loud: that what we're looking at isn't just behaving like a comet, it's behaving like something that was built to last. Most people imagine a comet's tail as a simple thing, a glowing trail of gas and dust, pointing away from the sun, streaming out like a flag in the wind of solar radiation. And for most comets, that's accurate. The solar wind blows outward, and the tail flows in the opposite direction of the sun, no matter which way the comet is moving. But 3I Atlas has never followed the usual rules, and now it's presenting a tail that shouldn't even exist. It's called an anti-tail, a strange optical illusion that occurs when the geometry between Earth, the comet, and the sun aligns in a rare way. From our point of view, it looks like a tail pointing toward the sun instead of away from it. Most of the time, anti-tails are faint, short-lived, and only appear near opposition when Earth crosses the comet's orbital plane. But with 3I Atlas, the anti-tail is not faint, it's growing, intensifying, and lasting far longer than any known example. The first detection of the anti-tail came in late November when amateur astronomers began reporting an unusual structure opposite the main tail. Initially dismissed as an imaging artifact, the reports became harder to ignore when major observatories confirmed the same shape from multiple vantage points. Then on December 3rd, high-resolution imaging from the Subaru telescope revealed a sharply defined, sunward-pointing plume, narrow, coherent, and shockingly bright. This is not normal. In natural comets, anti-tails are formed by large, slow-moving dust particles that spread along the comet's orbital path and reflect sunlight when viewed edge-on. They are passive structures, leftovers, not active emissions. But 3I Atlas's anti-tail is behaving more like a jet. It's directional, it's sustained, and it seems to pulse. Researchers have now tracked its evolution over several nights and found something even more unexpected. The anti-tail is not fixed to the orbital plane. It wobbles, it arcs slightly northward, then returns. This suggests the material isn't just floating in space, it's being pushed, and the only force that could be pushing it is coming from the object itself. That's the moment many astronomers went silent. Because if a sunward pointing tail is being actively maintained, not just optically generated, it implies a reversal of pressure, an emission or propulsion occurring toward the sun. In known physics, that doesn't make sense. Solar wind and radiation always push particles away from the sun. They don't allow structures to persist in the opposite direction. Unless those particles are heavy, slow, or magnetically bound, and that's where new theories are forming. One hypothesis suggests that the antitail is composed of metallic grains or charged particles, far denser than typical comet dust, released in a slow, steady stream along a guided vector. In this view, the antitail may not be a relic, it may be a stabilizing force, a way for the object to balance or correct its orientation as it navigates gravitational and solar wind forces. It would be less of a tail and more of a thruster. Another, even bolder idea is that the anti-tail is a communication signature, a structured emission designed to be visible only from Earth's vantage point. The geometry required to produce such a visible, coherent anti-tail at this scale is narrow and rare. The fact that it formed precisely during Earth alignment raises questions that feel increasingly intentional. The core problem is that comets do not aim things. They release material randomly, messily, in every direction. But 3I Atlas appears to be aiming, or at least emitting, in ways that are geometrically meaningful. The anti-tail is not just beautiful, it's not just rare, it's not just bright. It's directed, and that suggests we may not be looking at exhaust, but intention. In the vast spectrum of electromagnetic radiation, the L band is relatively quiet. Nestled between 1 and 2 gigahertz, this frequency range is often used for radar, GPS, satellite communication, and deep space observations. It's prized in astronomy for its ability to penetrate dust and gas with minimal distortion. And because it's such a clean slice of the spectrum, it becomes immediately obvious when something strange appears within it. On the morning of December 4th, that's exactly what happened. Multiple radio observatories, including Arecibo's successor facilities in the Caribbean and the Allen Telescope Array in California, began picking up faint, repeating signals bouncing back from the direction of 3I Atlas. These weren't transmissions, they were reflections, echoes, specifically radar pings sent toward the object as part of an ongoing observation campaign to map its structure and spin. And the returns were not normal. Normally, a radar ping sent to a comet produces a messy return. The surface is irregular, covered in ice and dust, and the signal bounces off at random angles, producing noise rather than clarity. But 3I Atlas responded differently. Its L-band radar profile returned a series of sharp, coherent reflections, consistent in strength, shape, and timing, suggesting smooth surfaces or even angular structures that reflect predictably. Even more unusual, these echoes were modulated, not electronically, but physically. The shape of the return varied on a consistent cycle, synchronized with the object's rotation rate as previously measured through light curve analysis. This implies that the reflecting surfaces aren't randomly distributed across the body. They're organized, repeating, geometrically spaced. This behavior has only been seen once before, and that was with metal-rich asteroids known to have flat facets or plateaus, but even those objects return weaker echoes than what 3I Atlas is producing. The strength and cleanliness of these L-band reflections suggest something unprecedented. Either the object is coated in a highly reflective material, or it's made of it. One theory proposes that the surface of 3I Atlas contains layers of conductive carbon, a structure similar to heat tiles used in spacecraft shielding. These would reflect L-band frequencies with unusual efficiency, especially if arranged in a patterned array. Another possibility is a naturally occurring but highly unusual crystalline lattice, though no known comet or asteroid has ever produced this kind of radar echo pattern. The most radical idea, currently discussed only in closed circles, is that we're not seeing natural radar reflection at all, but the byproduct of artificial geometry, that the object's symmetry isn't coincidental, that the repeating intervals in the radar return are signatures of compartmentalized structure, panels, ribs, or even internal bracing that happens to reflect L-band in just the right way. Supporting this, a brief pulse return was recorded with timing that aligned to a sudden brightening in the coma, a flash of reflected light in the visible spectrum, immediately followed by a peak in the radar signature. No one is calling it a response, not officially, but the correlation is now being tracked closely. If these patterns persist, 3I Atlas may soon be known not just for its brightness or trajectory, but for being the first interstellar object with consistent radar behavior, something that could change how we detect and classify spaceborne visitors moving forward. And while no one is saying the word technology just yet, the silence between observers, especially at NASA and ESA, is growing louder by the hour, because echoes imply structure, and in the L-band, structure is hard to fake. The James Webb Space Telescope wasn't built for comets. It was built for galaxies, exoplanets, and the earliest light in the universe. But when an object like 3I Atlas starts acting like nothing we've seen before, changing course, defying thermal norms, and emitting structured L-band echoes, even a billion-dollar observatory turns its attention closer to home. On December 2nd, the Webb telescope locked onto 3I Atlas during a scheduled window approved by NASA's director's discretionary time. The plan was clear: a full spectroscopic pass using the NIRSpec instrument to study the object's reflected infrared spectrum across multiple wavelengths, followed by deep field imaging to resolve structural detail in the coma and nucleus. But the observation didn't last. Roughly 41 minutes into the scheduled session, the telescope switched targets. That sudden shift caught researchers off guard, including the observing team who had petitioned for the data. At first, it was assumed that a technical error had triggered the cut. JWST does carry strict thermal and mechanical constraints, and sometimes automated safeguards override custom observation scripts. But when requests were made to resume or reschedule the observation, silence followed, and that silence has not broken. As of the morning of December 4th, no additional windows have been scheduled for 3I Atlas. The official report from the Webb mission team cites instrument prioritization and updated target constraints, vague language that in scientific circles often signals an internal classification or redirection. In simpler terms, someone higher up made a call. The limited data that was captured before the session was cut has now been partially leaked through secondary collaborations, and what it shows is troubling. The spectral fingerprint of 3I Atlas in the near-infrared is highly inconsistent with natural cometary material. There's a strong flat reflectance in regions typically associated with carbon-rich volatiles, but without the characteristic water absorption troughs. In other words, the Webb saw carbon, but no water, reflectivity, but no scatter. And worse, the object's infrared glow was polarized. That implies the surface is not only smooth, but possibly structured, reflecting infrared radiation directionally, a trait seen in manufactured materials like solar arrays or thermal control blankets, not in cosmic ice balls. These findings make the observation cut all the more suspicious. It's not just that the session ended. It's when it ended, right after the first deep imaging sweep began, just before the object would have moved into optimal frame for high-resolution composite stacking. That's the moment where shape could have been resolved. geometry could have been confirmed, and any suggestion of symmetry or structure would have become visible not just to professionals, but to the public, as web data is eventually released to open archives. But now that data may never reach public hands. Independent astronomers have begun cross-referencing the official JWST observation logs and several note a pattern. When certain types of anomalies are flagged in early imaging, follow-up sessions often vanish without explanation. One researcher, speaking anonymously, described it bluntly: "There are things Webb is allowed to look at and things it is allowed to see. Those aren't always the same." What 3i Atlas did during that short Webb window may never be officially acknowledged, but among the few spectrographs that escape the black box, the implications are already forming. This object does not reflect like a comet. It does not behave like a comet, and now it's being treated like something more sensitive. When the most powerful telescope ever launched is told to look away, mid-session, mid-transit, mid-discovery, the silence becomes the signal. And sometimes what isn't shown tells the whole story. In space, motion is truth. Every fragment, asteroid, or comet follows a chaotic dance, wobbling, spinning, precessing, especially when it's irregularly shaped. These small bodies tumble naturally, governed by basic physics, inertia, gravitational nudges, and uneven outgassing. It's chaotic, it's messy, and it's universal, except when it's not. 3i Atlas, despite all expectations, is not tumbling. For the past several weeks, light curve analysts have been watching closely, tracking the variations in brightness that tell us how an object rotates. If a comet or asteroid spins unevenly, its surface reflects sunlight at changing angles, creating a rhythmic pattern of dimming and brightening. That's how astronomers deduce shape, spin period, and rotational behavior. But 3i Atlas has broken that rhythm. From multiple observatories in Chile, Hawaii, and even amateur arrays across the southern hemisphere, the reports have converged. The brightness curve is flat, not constant in absolute terms, but stable in phase. The object's brightness varies only slightly and always in the same direction. Over days, over weeks, there is no flip, no oscillation, no precession. It is not tumbling, it is holding orientation. That shouldn't be possible, especially not for an interstellar object believed to be asymmetric and under solar pressure. At this distance from the sun, any small comet-like body would be experiencing measurable torque from uneven outgassing, from solar wind, from the slightest asymmetry in shape, and yet 3i Atlas remains locked. One theory suggests that the object's shape may be nearly symmetrical, perhaps a long ellipsoid with mass distributed perfectly along its axis. But even then, thermal irregularities and outgassing would gradually induce torque. Another possibility is internal damping, a phenomenon where liquid or semi-liquid interiors reduce tumbling over time. But for that to occur, the object would need to retain significant internal heat, and 3i Atlas has shown no evidence of that. Then there's the third theory, that it's actively stabilized, that this object is either using internal mass balancing or a controlled orientation system to maintain its facing. This is not science fiction. Spacecraft use similar systems, momentum wheels, gyroscopes, and even small thrusters to maintain precise orientation over long periods. Could something similar be happening here? The evidence adds weight to that idea. Observers noted that the light curve reflects not just consistency, but intention. The object seems to hold its brightest reflective surface always toward Earth, even as it moves through space. That's more than stability. That's alignment. That's orientation with context. Could it be a coincidence? Of course. But if it is, it's one of the most statistically unlikely alignments ever recorded. A non-tumbling object maintaining a fixed facing across multiple weeks during solar approach and through gravitational transitions. This leads to another important implication. If 3i Atlas is not tumbling, it may also be navigating. A tumbling body is difficult to steer, a stable one is ready to maneuver, and with the trajectory shifts already recorded, that possibility grows harder to ignore. The absence of tumbling is not just a curiosity, it's a constraint. It removes random motion from the equation. It means that every action this object takes, every shift in trajectory, every pulse of gas, every beam of reflected light is coming from a stable platform. And that stability suggests either extreme natural luck or extreme control. In a universe full of spinning rocks, one object stands still, and that stillness in motion speaks volumes. The first time it happened, many thought it was a glitch, a calibration issue, a sensor flare, or just another coincidence in a sky filled with noise. But when it happened again and again, the excuses began to unravel. And now the reflective flash pattern has returned. For the third time since 3i Atlas entered observational range, astronomers have documented a series of sharp, rhythmic optical flashes reflecting off the object's body, each one lasting no more than a few seconds, but following a highly specific sequence. From three different observatories, one in Spain, one in Hawaii, and a remote station in Chile, the same thing was seen. Pulses of light, spaced evenly, coming from a fixed region on the object, and repeating every 94 minutes. This isn't random. Natural objects, especially tumbling ones, occasionally produce glints when the angle of the sun and observer align with a flat surface. It's how some defunct satellites blink across the sky, and even how Oumuamua created brief speculation back in 2017. But those glints are irregular, one-off events that never return with precision. This is different. The flashes are narrowband in the visible spectrum. They are coherent. They return in a fixed sequence, and critically, they only appear when the object is within a precise angular window relative to Earth. That window moves predictably based on 3i Atlas's orientation and position, meaning the reflections are not passive. They're positionally dependent. They are synchronized with geometry. In other words, they're behaving like a signal. The intensity of each flash is not blinding, but sharp, easily separated from background light. Spectral analysis shows a highly reflective surface at the source, potentially metallic or crystalline in nature. No known cometary surface reflects light in this way. Not ice, not rock, not carbon dust. And they're directional. When one observatory sees the pattern, another, just a few thousand kilometers away, sees nothing. That kind of locality suggests the flashes are not wide-angle beams, but tight reflections, pinpoint alignments, the kind of thing you would expect from something mirror-like or structured or aimed. Some researchers have proposed a natural explanation, perhaps a large, flat surface, like a sheared fragment or slab, is rotating slowly, producing a repeated glint, but this theory fails under scrutiny. A rotating fragment would create irregular flashes with slowly shifting intervals. What 3i Atlas is showing instead is precise, down to the second. Even minor trajectory changes haven't affected the cycle. Others have suggested solar panel analogs, not literal panels, but flat mineral surfaces forming naturally. Yet again, no known comet in recorded history has demonstrated this. And even if one did, the alignment would have to be perfect repeatedly for the same pattern to return. This brings back a haunting memory from weeks earlier when a similar flash pattern appeared just before perihelion and then abruptly stopped. At the time, it was dismissed as solar interference, but now it's returned, stronger and lasting longer. And now there's a new layer to the mystery. Observers recorded a spike in the L-band radar profile exactly 17 seconds after the second flash in the sequence, a faint echo like a delayed answer to a knock. No one knows if the two are connected, but the timing is too close to ignore. If the flash pattern is intentional, and that's still a word scientists hesitate to use, then 3i Atlas is doing more than drifting through space. It's broadcasting something, maybe not a message, maybe not for us, but it's performing a behavior that no ice ball ever has, a repeating pattern, a return of light, and a question that no one has the tools to answer, but everyone feels in their gut. Who or what is blinking back? When we think about comets, we rarely think about magnetic fields. Traditional comets don't generate their own magnetospheres, they simply pass through the suns. And as they move, their ionized gases interact with solar wind, forming long plasma tails that are swept back by the sun's charged particles. It's reactive, not active. But with 3i Atlas, that assumption no longer holds. On the morning of December 4th, several monitoring stations, including those operated by ESA's Swarm satellite cluster and the magnetometer arrays across the equatorial belt, reported something strange, a localized compression in the magnetic field lines around the projected path of 3i Atlas. Not a solar storm, not a global shift, a targeted narrow disturbance with a footprint far too small to be solar in origin. This kind of compression has only been seen before in one context, when a fast-moving object with either an intrinsic or induced magnetic field passes through ambient solar plasma. In that context, compression forms on the leading edge of the object, a bow shock, while a wake forms behind. But here's the problem. Comets shouldn't generate bow shocks like this unless they're highly charged or moving against the flow of solar wind, and 3i Atlas was aligned with the solar wind. That leaves a few possibilities, and none of them are easy to explain. The first possibility is that 3i Atlas has somehow developed an induced magnetosphere, a magnetic field created by the interaction between its surface and solar particles. While this does occur on some planetary bodies like Venus, it's incredibly rare for objects of this size, especially those not wrapped in a dense atmosphere. The second possibility is even more intriguing, that the object has an internal magnetic structure, perhaps a core with remnant magnetization or active electrical flow. This would suggest a far more complex internal makeup than ice and dust. It implies metal, structure, possibly even compartments or conduits capable of holding and redirecting charge. But the most radical theory is that the compression isn't passive at all, that 3i Atlas is generating the field deliberately, not by accident, not by composition, but through intent, as if shielding itself or manipulating the space around it to maintain trajectory control. And this is where things start to cross a line, because magnetic shielding is not just a theoretical concept, it's one of the cornerstones of advanced spaceflight design. Magnetic bubbles have been proposed as protection against solar radiation and micrometeoroids. They've also been explored as a way to reduce drag or steer through charged environments. But in every case, it requires energy, systems, intelligence. So when an object from another star system begins showing signs of localized magnetic compression, people notice. And when that compression shifts, moving slightly ahead of the object's leading edge, as if adapting, people start asking very different questions. What is it protecting against? What is it hiding? And why is it only now becoming visible? The fact that the compression is localized means something is interacting with the solar environment in a controlled footprint. Natural comets expand their influence as they outgas. They get messy, but 3i Atlas remains sharp, clean. It's as if the magnetosphere is not a byproduct, but a suit fitted tightly, reshaped constantly, and adapting in real time. And perhaps most telling, the compression is now ahead of the predicted path, as if it's preparing for something, or approaching something, or more chilling still, targeting something. Whatever 3i Atlas is, it is not just surviving in the solar system. It's negotiating with its environment altering it, shielding its body in ways we've never seen from any natural object before. This is no tail, no coma, no drift of dust. This is pressure, direction, defense, and it may be a sign we're getting close to the next phase, one where the object no longer hides in shadows of passive motion, but starts to assert its place in our space. Not everything makes the news. And in the world of space agencies, not everything is meant to. On December 3rd, a short encrypted bulletin was circulated internally across multiple European research institutions, flagged Class 3 contingency notice, and stamped with the European Space Agency's internal observatory seal. The subject line was vague. Trajectory adjustment confirmed. 3I Atlas. But the attached summary told a more alarming story. ESA's internal orbital models, updated with fresh data from their deep space antenna in Cebreros, Spain, had confirmed something quietly discussed in private circles for days. 3I Atlas had altered course again, and not slightly. The new trajectory placed the object on a tighter path through the Earth-Moon system corridor with a point of minimum distance arriving near December 19th. Not a direct hit, not even a close shave in astronomical terms, but close enough and precise enough that senior analysts flagged it for system-wide signal continuity preparation, a cryptic phrase that essentially means prepare for potential disruption. But the public never heard about it. By December 4th, no press release had been issued, no updated orbital tracks were posted to ESA's public-facing NEO dashboards, and the internal bulletin, once leaked by a university researcher in Belgium, was quickly scrubbed from all online mentions. Even the original email thread, archived through institutional servers, now shows as expired token. And this is not the first time it's happened. Back in late November, ESA's Plato observation team had logged a sudden dip in optical reflectivity from 3I Atlas, a shift that indicated surface behavior or rotational change. That data never reached public discussion. When asked, the agency responded with a templated reply, data not validated for public distribution. But this latest warning is different because of what it implies. ESA isn't prone to overreaction. They operate with layers of peer review, checks, and national protocols. A Class 3 tag does not go out lightly. It's reserved for mission-impacting events, usually solar flares, debris field expansions, or tracking anomalies. For an interstellar object to be flagged under this level means one thing: it's no longer being treated as passive. So why no public statement? The official explanation from ESA's media office, when questioned anonymously, was that all data relating to 3I Atlas remains under evaluation and is being processed through standard collaborative channels. But off the record, one mission analyst put it more bluntly: we're not in charge of this story anymore. And that's what makes this so unsettling, because this isn't just about data, it's about control. The moment an object's behavior exceeds prediction, when it shifts faster than our models can adapt, or moves as if responding to forces outside classical dynamics, it stops being an observation and becomes a liability. And for agencies tasked with global coordination, ambiguity is the one thing they can't afford to acknowledge. So the warnings go unpublished, the tracking becomes classified, and the data pipeline narrows from public science to quiet briefings behind closed doors. There are rumors, of course there are, that NATO satellites have picked up heat signatures near the object, that internal memos are being drafted by civil defense councils, that even the Vatican's observatory has flagged its December track as non-standard. But none of these claims are confirmed, and none will be. What is confirmed from the bulletin that did leak is that ESA now recognizes 3I Atlas as a variable trajectory object, not natural, not predictable, and no longer treated as just a comet. Whether this was the plan from the beginning or a shift triggered by something we don't yet understand, one thing is now certain: the story is changing, And some agencies are doing everything they can to make sure you don't see how. Comets fade. That's what they do. After perihelion, the closest approach to the sun, every known comet begins to dim. The heat wanes, the gas jets slow, the coma dissipates, and the light curve falls. This is the natural rhythm of these icy travelers. Their brilliance is temporary, a flare of vapor and dust before they slip back into shadow. But 3I Atlas is doing something different. Since passing closest to the sun over a week ago, astronomers around the world expected the object's luminosity to drop. Instead, it's holding, in fact, in certain observation bands, particularly in infrared and narrowband green, the object is slightly brighter than it was 3 days prior. That makes no sense. In the case of natural comets, outgassing is tied to solar proximity. The further they get from the sun, the less energy hits their surface and the weaker their gas jets become. The coma, the glowing cloud of evaporated material, thins, fades, and eventually disappears. But the coma around 3I Atlas is not dissipating. It's staying intact, even sharpening in spectral consistency. So where is the energy coming from? Some observers have proposed that 3I Atlas may be undergoing a kind of delayed heating, that its internal structure could be absorbing heat more slowly, then releasing it post-perihelion like a thermal capacitor. But if that were true, we'd expect thermal lag effects in the infrared data. We don't see those. The heat output is stable, not delayed, not decaying. Others suggest that perhaps the object is undergoing a secondary outgassing phase where volatile ices beneath the surface are now reaching sublimation thresholds, but even that fails to explain the consistency of the light output. There's no fluctuation, no surging or trailing off. It's controlled, steady, unnatural. And then there's the coma itself. Images from multiple observatories have shown something disturbing. The coma doesn't behave like a natural dust cloud. It doesn't spread chaotically. It doesn't diffuse with solar wind. Instead, it appears structured, layered in fine gradients with boundary lines that stay rigid even under plasma pressure. Some have even described it as shield-like or encapsulated, a word never before used to describe a comet's wake. What we're seeing is not the slow death of a fading object. We're seeing maintenance. It's as if something is keeping the system alive, replenishing, stabilizing, adjusting its thermal footprint, and maintaining its light profile, as if trying not to disappear. This raises a haunting question. Why would an object want to remain visible? For most natural bodies, brightness is an accident, it's byproduct, but for a constructed or controlled system, visibility might be a feature, a signal, a warning, or even a test. Some researchers have even speculated in closed forums that the consistent luminosity may be modulated, that we're not just seeing a reflection of sunlight, but an emission pattern, something radiating deliberately. But what confirms the anomaly isn't just brightness, it's contrast. During this same week, two other comets, both similar in size and position, have dimmed as expected. One comet D96P dropped by 18% in visual brightness in 4 days. The other, B4C Tholen, is now nearly invisible in the green spectrum, but 3I Atlas still shining, still holding position, still resisting decay. The object refuses to fade, not just in light, but in behavior. It continues to break patterns, defy comparisons, and act in ways no natural body ever has. And perhaps that's the answer itself. Maybe fading isn't part of its life cycle. Maybe this isn't an object built to appear now, then vanish. Maybe this is the beginning of its presence, and fading was never the plan. It started as a glitch, or at least that's what analysts first assumed. The Solar and Heliospheric Observatory, better known as SOHO, has been orbiting between Earth and the Sun since 1995, monitoring solar flares, sunspots, and coronal mass ejections. But on December 4th, one of SOHO's coronagraphs picked up something it wasn't designed to see, a duplicate signal near 3I Atlas. At first glance, the object appeared to be a reflection, a brief echo of light and plasma where there shouldn't be one, but this wasn't just an artifact. It persisted for several imaging frames at consistent intervals and at a measurable offset from the main object, approximately 120,000 kilometers to the rear and slightly below the orbital plane. The team tagged it as a secondary signature. This might not seem unusual. Comets often shed fragments. Pieces break off under stress, forming smaller bodies that trail in their wake. But those fragments behave chaotically. They drift, they tumble, they brighten and fade. This one didn't. It moved in lockstep. Frame after frame, the secondary object matched the speed, the angle, and even the magnetic bow structure of the primary body. It maintained a fixed distance and alignment as though tethered. No deviation, no drift. That's not fragmentation, that's formation. Immediately, researchers began asking whether this second signature could be a companion body, not a breakaway, but a coordinated object traveling with 3I Atlas. Binary system, a two-part vehicle, or worse, a deployment, because here's what truly breaks the pattern. The signal only appears in SOHO's coronagraph images, not in optical telescopes. That means it isn't reflecting visible light. It's interacting with plasma, specifically solar wind particles. It's visible only in the charged particle environment near the sun, like a magnetic object revealing itself only when struck by energy. Some analysts noted the similarity to spacecraft ion trails, the faint plasma signatures left by certain types of high-velocity propulsion. In that context, the second object wouldn't be a rock, but a device, a stabilizer, or a probe. More data was gathered. SOHO's LASCO C3 instrument picked up faint turbulence patterns between the two bodies, curved arcs of solar plasma moving from one to the other, almost as if there was a connection, magnetic or electrical, bridging the two. The pattern wasn't random. It pulsed in waves. By the end of the day, ESA's internal logs had marked the anomaly as a synchronized plasma interaction, a phrase never before used in the context of a comet, but perhaps most chilling was what happened after. The secondary signature vanished, not drifted, not faded, gone in one frame to the next, like a switch had been flipped. One moment there was a clear, persistent trail, the next, silence. It hasn't been seen since. That disappearance makes it even harder to classify. If it were a natural fragment, it would still be trackable. It would reflect, scatter, decay. But there's no optical follow-up, no radar ping, no thermal ghost, just a momentary presence seen only under the unique conditions of the inner heliosphere and then withdrawn, which leaves us with a question that few are willing to ask aloud. Was that second object always there? Is 3I Atlas flying solo or accompanied? And if there's more than one, what are we really watching? Because this changes the story. A comet is one thing, but a formation implies planning, coordination, strategy. It implies intent. And if SOHO's glimpse was real, if that second signature was not a coincidence, not a dust cloud, not a reflection, then everything we thought we knew about 3I Atlas must be reconsidered. It may not be an object, it may be the lead object. Most dates in astronomy are just milestones, timestamps on a map of motion, but every so often a date emerges that's more than just a moment. It becomes a convergence. And in the case of 3I Atlas, December 19th is exactly that. At first, the date seemed arbitrary, just another marker along its trajectory. But when orbital analysts across ESA, NASA, and Japan's JAXA superimposed multiple planetary, lunar, and solar magnetic layers, something strange appeared. The object would intersect a temporary corridor of gravitational neutrality, a rare moment where multiple celestial influences cancel each other out. This corridor is called a transient orbital equilibrium zone, and it doesn't last long, just a few hours at most, but during that window, space becomes different, lighter, looser, objects move differently, forces become subtle, even silent, and any anomaly, any deviation becomes amplified. December 19th is the exact center of that window, not before, not after, just then. On that date, the gravitational influence of the Earth, the Moon, and the Sun briefly fall into phase. It's not that gravity disappears, it's that the push and pull line up in such a way that the space around 3I Atlas becomes unusually forgiving. An object with any form of propulsion, natural or otherwise, could adjust direction with minimal energy. A slight nudge could redirect a massive body with precision. In spaceflight, this is the equivalent of catching a windless corridor just before the storm returns. But what makes this more unusual is how perfectly 3I Atlas aligns with it. Astronomers are used to rough approximations. Space is messy, and comets rarely hit predicted paths with such accuracy. Yet this object, whose previous motion has already defied classical dynamics, is set to enter this precise zone within hours of its strongest potential. The margin of error? Less than a quarter degree. How does something like that happen? Was it coincidence or something else? The idea that 3I Atlas is on track to reach Earth has always depended on small fluctuations, gravitational nudges, solar radiation pressure, and dust ejections. But the alignment with this orbital synergy point changes the stakes. It's no longer just on track. It's surfing the edge of a celestial moment that makes subtle movement easy and observation difficult. What does that mean? It means this is the perfect moment for a maneuver. If the object were to shift, slow down, speed up, or even deploy something, this corridor would allow for maximum impact with minimum trace. A change in trajectory made on December 19th would ripple outward smoothly, bypassing the usual detection filters because gravitational models assume resistance, and on this day there isn't any. And here's where the tension builds, because the last time Earth passed through a similar zone was over a decade ago, and nothing was in the vicinity to exploit it. This time something is, and it's not just nearby. It's moving into the center of the corridor with elegant timing. Too elegant, some would say. Observers are beginning to ask the obvious. Is 3I Atlas aware of this? Or more accurately, is it following a course designed to use it? Because if so, this isn't a passive object floating through a random solar system. This is an insertion, a coordinated arrival into a gravitational nexus, a chess piece, making its move not just on the board, but on the very geometry of the board itself. December 19th isn't just a date. It's the moment the board clears and something chooses its next direction. The vacuum of space, every motion leaves a trace, not a footprint, but a wake, a trail of dust, gas, or energy that lingers behind a moving object. For comets, this wake is expected. It's the debris of sublimating ice, volatile outgassing, and gravitational shearing. And just like smoke from a flame, it should spread, thin out, and eventually disappear. But the wake behind 3I Atlas is not behaving like that. It's not fading. It's not spreading. It's holding together like a thread stretched tight across the solar wind. Since 3I Atlas exited perihelion, multiple observatories, including SOHO, STEREO, and even civilian astrophotographers using polarization filters have been tracking its tail structure. What they've observed is deeply unsettling. The wake behind the object is not dispersing like natural ejecta. It remains narrow, dense, and perfectly aligned with its orbital track. In simple terms, it's too clean. Cometary tails are chaotic. Particles get blown sideways by the sun's radiation, pushed outward in curling arcs. But this wake moves with 3I Atlas like a tether, not like something it shed, but like something it needs. What's more, the wake exhibits non-random oscillation. One station in Argentina detected repeating pulses in the tail's density every 7 minutes. That's not a natural resonance, not from a rotating body or jetting activity. It's a rhythm, a clockwork pattern. It suggests a system modulating pressure, perhaps even synchronizing its output, and that raises serious questions. Is the tail intentional? We've always assumed comet tails were waste, evidence of decay. But in this case, the waste appears organized. It holds structure across hundreds of thousands of kilometers. In spectroscopic readings, the dust shows unusually uniform particle sizes, as if filtered. There are no large chunks, no irregularities, just micron-level grains perfectly suspended. And that uniformity suggests something unprecedented, tail management. But for what purpose? Some theorize it's a form of plasma steering, a method of using charged particles in the solar wind to create directional resistance. Others believe it may be reflective camouflage, blending the object's thermal signature into the heliospheric background. But one theory, whispered only in private Slack channels and encrypted message boards, goes further. What if the wake isn't trailing the object? What if it's anchoring it? The idea sounds impossible until you remember that Earth-based satellites use ion plumes to maintain orientation, and in deep space physics, a narrow band of charged material can, under the right conditions, create a reactive force against solar wind. It wouldn't be propulsion in the traditional sense. It would be resistance-based positioning. Think less rocket, more sail. And that makes the lack of dispersion even more critical, because if this object is actively generating a stable wake to maintain balance or direction, then we're not just observing a strange comet, we're observing a stabilized system, a craft, or at least a guided object. And the deeper problem, the wake is growing. Latest imagery shows the structure extending backward at a fixed velocity, retaining shape and density across increasing distance. That kind of consistency suggests ongoing emission, not just from perihelion outgassing, but from a system still operating, still releasing, still maintaining shape, well beyond what's expected. The wake doesn't drift. It holds position. It follows like a shadow that obeys. And in doing so, it tells us something we didn't want to believe. 3I Atlas is not being pushed by the sun. It's navigating through it. There's a point in every astronomical event when the silence breaks, when quiet speculation becomes urgent coordination, when institutions that typically compete begin to whisper the same questions in different languages. That point has now arrived across the globe. From NASA's Jet Propulsion Lab in California to China's Purple Mountain Observatory, from the South African Large Telescope to the deep space arrays in Japan, the same object has become the singular focus of an otherwise fractured scientific world, 3I Atlas. And not because it's bright, not because it's beautiful, but because it's unexplainable. Since early December, the object has moved in ways that resist every classical model. It has refused to slow when expected, refused to rotate as predicted, and revealed piece by piece a behavior pattern that seems not random, but deliberate. Scientists are no longer asking what it is, they're asking what it's doing. And as December 19th approaches, that urgency is escalating. Internally, multiple agencies have shifted protocol. Observations that were once scheduled weekly are now happening hourly. Time allocations on major telescopes are being quietly overridden. Even the James Webb Space Telescope, which normally plans its movements years in advance, is rumored to have repositioned for a classified mid-infrared capture attempt, although no official statement confirms this. Amateur networks are seeing the change too. Online forums dedicated to astrophotography, usually buzzing with debates about filters and calibration, have turned into live feeds of trajectory modeling and thermal overlays. Reddit threads show side-by-side comparisons of 3i Atlas across the electromagnetic spectrum, while Discord servers once focused on exoplanets are now flooded with speculation about controlled deceleration and wake harmonics. The language has changed. We're no longer observing a comet. We're tracking an object of interest, and that term isn't used lightly. In defense and aerospace circles, object of interest is a label reserved for targets that demonstrate unclassified behavior but classified concern. It's the same phrase once used for the first known satellite maneuvers by China's SJ-21. Now it's being attached to something interstellar. Why? Because even now, 3i Atlas refuses to follow the script. Its infrared signature remains constant. Its tail shows directional modulation. Its approach vector continues to align with a gravitational window that opens and then closes on December 19th. And in its shadow trail, researchers are still parsing unexplained plasma pulses and brief magnetic echoes. It's as if the object is broadcasting a low-level signal, not to us, but to something. And it's not just scientists watching anymore. Intelligence agencies have taken notice. Leaked documents hint at involvement from surveillance satellites tasked with tracking heat blooms and particle anomalies. Some insiders claim that certain space-based sensors have been realigned, not toward Earth, but toward deep space, toward the corridor 3i Atlas is now entering. Even pilots and commercial airlines have been issued quiet notices to report any high atmosphere light fluctuations between specific latitudes in the coming days. No official explanation is given, but the implication is clear. Everyone's watching now. Because whether this is a natural anomaly or something far more constructed, the stakes have changed. Earth has entered the conversation, not just as a bystander, but as a reference point. Every satellite, every lens, every eye turned skyward is now tracking one question: what happens next? And the truth is, nobody knows. We've sent probes to the edge of the heliosphere. We've mapped the surface of moons orbiting Jupiter. But never, not once, have we watched something from outside this solar system move with intention until now. And as 3i Atlas approaches its final orbital corridor, every instrument we have is locked on, not to stop it, not to alter it, but simply to understand, because some truths don't arrive loudly. They arrive slowly, and then all at once.